September 14, 1943, 11:47 hours, and Hauptmann Klaus Weber, commanding 2nd by JG-26 6th Staffel, adjusts his Focke-Wulf 190A6's trim as he climbs through 24,000 feet over the German-Belgian border. Behind him sits 14 millimeters of hardened steel armor plating that has deflected dozens of Allied machine gun rounds during his 18 months of combat flying. His fighter's armored cockpit, engine protection, and fuel tank shielding represent the pinnacle of German aviation metallurgy, designed to withstand anything the Allies can throw at him from their primitive 50-caliber machine guns. Before we jump back in, tell us where you're tuning in from. And if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. What Hauptmann Weber cannot possibly know, what no German pilot could imagine in their most confident moments, is that American ammunition engineers at Frankfurt Arsenal have revolutionized .50 caliber ballistics through tungsten carbide cores and incendiary compounds that transform supposedly harmless machine gun rounds into armor-piercing projectiles. Within minutes, these inadequate American bullets will punch through his trusted armor plating like tissue paper, their 2,900 feet per second velocity and tungsten cores turning German fighter protection into deadly fragments that kill pilots faster than enemy fire. The 14-millimeter steel plate that Weber considers his guardian angel will become his executioner as American ammunition technology renders German armor obsolete in a spray of molten metal and superheated gas. The Luftwaffe's faith in their aircraft armor systems comes from 2 years of combat experience demonstrating the effectiveness of German metallurgical science applied to pilot protection. The systematic development of armored cockpits, self-sealing fuel tanks, and engine protection has created German fighters that can absorb punishment while remaining operational, giving pilots confidence that their aircraft will bring them home despite enemy fire. Hauptmann Weber's Focke-Wulf 19A6 represents the evolution of German fighter protection through multiple design iterations that have strengthened vulnerable areas while maintaining flight performance. The 14-millimeter armor plate behind his seat, manufactured by Krupp Steel using advanced heat treatment processes, has been tested against captured Allied ammunition to ensure adequate protection against .50 caliber machine gun fire at combat ranges. Preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video. It means a lot to us. Now back to the story. Oberleutnant Heinrich Müller, Weber's wingman with 26 aerial victories, has survived 3 emergency landings in fighters riddled with Allied machine gun holes that failed to penetrate critical armor protection. His experience reinforces German confidence in their protective systems while demonstrating the inadequacy of Allied ammunition against properly designed German armor plating. German armor development philosophy emphasizes protecting the pilot and critical aircraft systems rather than the entire aircraft structure, creating focused protection that maintains performance while ensuring survival. This approach allows German fighters to absorb significant battle damage in non-critical areas while protecting essential components from Allied fire that might otherwise prove fatal. The Focke-Wulf 19's armor layout reflects systematic analysis of combat damage patterns that identify the most likely impact areas for enemy fire. The pilot's back and head armor, combined with armored glass windscreen and side panels, creates a protective cocoon that deflects machine gun fire from the most common attack angles while maintaining visibility and control access. Major Friedrich Lusigkeit, commanding 2BII/JG-26, has compiled statistics showing that German pilots equipped with properly armored fighters have survival rates exceeding 85% when shot down, compared to less than 40% for unarmored aircraft. These figures validate German investment in pilot protection while demonstrating the life-saving effectiveness of advanced armor systems. German metallurgical advances in armor steel production have created materials that combine hardness with impact resistance, preventing the brittle failure that characterizes inferior armor under high-velocity impact. The heat treatment processes developed by German steel companies produce armor plates that deflect projectiles while maintaining structural integrity under repeated impacts. The psychological impact of armor protection extends beyond physical safety to pilot confidence that enables aggressive tactics against numerically superior Allied formations. German pilots attack Allied bomber streams with the knowledge that their armor can protect them from defensive fire, while Allied fighter pilots must respect German defensive capabilities. Lieutenant Werner Hoffmann, the youngest pilot in Weber's Staffel with 8 confirmed victories, has witnessed armor effectiveness during multiple engagements where Allied machine gun fire has failed to achieve penetration despite direct hits on his aircraft. His confidence in German protection systems reflects the broader Luftwaffe belief that German engineering superiority extends to defensive as well as offensive capabilities. German armor testing procedures involve firing captured Allied ammunition at armor samples under controlled conditions to verify protection standards and identify potential vulnerabilities. These tests consistently demonstrate that German armor can defeat Allied .50 caliber machine gun fire at all but the closest ranges, providing scientific validation for pilot confidence in their protective systems. The integration of armor protection with aircraft design ensures that defensive weight does not compromise flight performance beyond acceptable limits. German engineers have achieved optimal balance between protection and performance, creating fighters that maintain combat capability while providing pilot protection that exceeds anything available to Allied aircrew. German pilot training emphasizes using armor protection tactically by positioning aircraft to maximize defensive advantages while minimizing exposure to enemy fire that might overwhelm protective systems. Pilots learn to present armored aspects of their aircraft toward enemy guns while maneuvering to avoid prolonged exposure to concentrated fire that might overwhelm protective systems. What German intelligence networks have completely failed to detect is the revolutionary transformation occurring at American ammunition manufacturing facilities, where metallurgists and ballistics experts have developed .50 caliber projectiles that render German armor protection obsolete through advanced materials and innovative design approaches. The M8 armor-piercing incendiary round represents American industrial chemistry applied to the specific problem of defeating German fighter armor. The development of tungsten carbide cores for .50 caliber ammunition transforms standard machine gun projectiles into armor-piercing weapons capable of penetrating hardened steel plates that had previously provided adequate protection. American engineers at Frankfurt Arsenal have created projectiles that maintain their structural integrity at impact velocities exceeding 2,900 feet per second, generating kinetic energy sufficient to defeat 14mm armor at ranges beyond 400 yards. Dr. William Sterling, Chief Ballistics Engineer at Frankfurt Arsenal, has led the development program that combines tungsten carbide penetrator cores with incendiary compounds designed to ignite fuel and hydraulic systems after penetration. This dual-purpose ammunition achieves armor defeat while creating secondary effects that disable aircraft systems and endanger crew survival. The manufacturing process for advanced .50 caliber ammunition requires precision techniques that ensure consistent projectile quality while maintaining the high production rates necessary for military operations. American industrial capability enables mass production of tungsten-cored ammunition in quantities that make advanced projectiles available for routine use rather than special operations only. American metallurgical research has identified the optimal tungsten carbide composition for armor penetration, balancing hardness with impact resistance to create cores that maintain coherence during high-velocity impacts. This material science advancement enabled projectiles to punch through German armor while delivering incendiary payloads that create catastrophic secondary effects inside aircraft systems. The ballistics testing program conducted at Aberdeen Proving Ground involves firing experimental ammunition against captured German armor samples to verify penetration capability under combat conditions.
These tests demonstrate that advanced American projectiles can defeat German armor at ranges and angles that German designers never anticipated during their protection system development. Quality control procedures ensure that American ammunition maintains consistent performance standards despite mass production requirements that exceed German manufacturing capabilities. Statistical sampling and precision inspection techniques produce ammunition with reliability rates exceeding 98%, ensuring that American pilots can depend on their weapons' effectiveness against German armor. The integration of incendiary compounds with armor-piercing cores creates projectiles that achieve multiple effects through single hits, eliminating the need for mixed ammunition loads while maximizing target effects. The incendiary elements ignite fuel vapor and hydraulic fluid after penetration, creating fires that destroy aircraft systems and endanger crew survival. American industrial chemistry has developed incendiary compounds that remain stable during high-velocity impact while igniting reliably after penetration delay. These compounds burn at temperatures exceeding 4,000 degrees Fahrenheit, ensuring ignition of aircraft fuel and creating thermal effects that disable electronic systems and structural components. The packaging and distribution system for advanced ammunition ensures that American fighter squadrons receive adequate supplies of tungsten-cored projectiles for operational use. Unlike German special ammunition that must be rationed due to material shortages, American production capability enables routine employment of advanced projectiles against all suitable targets. Ballistics research conducted by American universities in cooperation with military programs has identified optimal projectile designs that maximize penetration while maintaining accuracy at combat ranges. These academic contributions enhance military ammunition development while ensuring that theoretical advances translate into practical battlefield capabilities. The cost analysis of advanced ammunition production demonstrates that American industrial capacity can absorb the expense of tungsten carbide cores and precision manufacturing while maintaining production rates that support operational requirements. This economic advantage enables sustained use of advanced ammunition while German forces face increasing material limitations.
Throughout 1942 and early 1943, German armor testing programs conducted at the Luftwaffe's technical facilities consistently validate the effectiveness of fighter aircraft protection against captured Allied ammunition, reinforcing pilot confidence in their defensive systems while failing to detect the advanced projectiles that American manufacturers have begun producing in increasing quantities. The test protocols employed by German engineers involve firing captured .50 caliber ammunition at armor samples under controlled conditions that replicate combat engagement scenarios. These tests demonstrate that standard Allied ball and armor-piercing ammunition cannot penetrate German fighter armor at typical combat ranges, providing scientific evidence that supports pilot confidence in their protection systems. Ober-Engineer Hans Becker, Chief of Armor Development at Focke-Wulf, has supervised extensive testing programs that confirm the adequacy of existing armor protection against known Allied ammunition types. His analysis indicates that German armor provides substantial safety margins against Allied machine gun fire while maintaining acceptable weight penalties that do not compromise aircraft performance significantly. German metallurgical analysis of recovered Allied projectiles reveals ammunition construction that German experts consider inferior to German armor-piercing designs. The examination of captured American .50 caliber rounds shows simple construction with steel cores that cannot match the penetration capability of German tungsten ammunition, reinforcing German assessment of Allied technological inferiority. The statistical analysis of combat damage reports supports German confidence in armor effectiveness by demonstrating high pilot survival rates despite extensive battle damage to aircraft structures.
German pilots routinely return from missions with aircraft showing multiple machine gun hits that have failed to penetrate critical armor protection, validating the design philosophy that prioritizes pilot survival over complete aircraft protection. Quality assurance procedures for German armor production ensure consistent protection standards across all aircraft production lines. The testing of individual armor plates before installation verifies that each component meets specification requirements for hardness, impact resistance, and ballistic protection, maintaining uniform protection standards regardless of manufacturing variations. German intelligence assessments of Allied ammunition production suggest that American manufacturers continue emphasizing quantity over quality in their projectile development. These evaluations indicate that Allied ammunition remains inferior to German designs while lacking the advanced materials and precision manufacturing that characterize German military production. The development of improved German armor designs focuses on optimizing protection against known Allied threats while reducing weight penalties through advanced metallurgy and design refinement. German engineers continue improving their armor systems based on combat experience and testing results that demonstrate consistent effectiveness against Allied weapons. Pilot feedback from operational units reinforces technical assessments by providing first-hand accounts of armor effectiveness under combat conditions. German aircrew consistently report confidence in their protection systems while describing multiple instances of Allied machine gun fire failing to achieve penetration despite direct hits on armored components. Training programs for German pilots emphasize the tactical advantages provided by superior armor protection, teaching aircrew to exploit their defensive superiority while engaging Allied fighters and bombers. This training creates tactical confidence that enables aggressive combat techniques based on the assumption that German armor can protect pilots from Allied defensive fire. The comparison between German and Allied armor protection systems demonstrates German superiority in both materials and design approaches. German analysis of captured Allied aircraft reveals inferior protection that confirms German technological advantages in pilot survival systems while validating continued investment in armor development. German production planning for fighter aircraft assumes continued armor effectiveness against Allied weapons, with resource allocation reflecting confidence in existing protection standards. The industrial planning process does not anticipate the need for significant armor improvements, reflecting German assessment that current systems provide adequate protection against foreseeable threats.
Within 20 minutes of the initial engagement, German pilots confront the terrifying reality that their trusted armor protection has become obsolete through American ammunition development that they never detected or anticipated. The systematic penetration of German armor by American .50 caliber fire creates tactical and psychological effects that extend far beyond individual aircraft losses. Hauptmann Weber's Focke-Wulf 190 suffers multiple armor penetrations that create a cascade of system failures as American incendiary rounds ignite hydraulic fluid, electrical systems, and fuel vapor throughout the aircraft. The armor that should have protected him becomes a source of additional hazard as tungsten fragments ricochet inside the cockpit, creating wounds that external hits would not have caused. All aircraft, American ammunition is penetrating our armor, Weber broadcasts on emergency frequency as he struggles to maintain control of his damaged fighter. Standard armor protection is ineffective. Avoid prolonged exposure to American fire and withdraw immediately if hit. The loss of Lieutenant Hoffman demonstrates the lethal effectiveness of American incendiary recovered from armor penetration sites demonstrate manufacturing quality and material science that exceed German estimates of American industrial capability. Major Losigkeit's after-action report acknowledges that German armor protection has become inadequate against advanced American ammunition, requiring immediate tactical modifications and urgent technical countermeasures.
His assessment concludes that German air operations must assume armor ineffectiveness until technical solutions can restore pilot protection. The strategic implications extend beyond immediate tactical concerns to fundamental questions about German fighter design and protection philosophy. The realization that American industrial capability can produce advanced ammunition in quantities sufficient for operational use suggests that German defensive advantages may be temporary rather than permanent.
Within days of the initial encounter, reports of American armor-penetrating ammunition spread throughout German fighter units across Europe, creating psychological effects that prove as devastating as the physical threat itself. German pilots who had considered themselves protected by superior armor technology suddenly faced the reality that their defensive advantages have been eliminated through American innovation. Oberstleutnant Johannes Steinhoff, commanding JG-26, convenes emergency briefings to address pilot concerns about armor effectiveness while attempting to maintain combat morale in the face of technological obsolescence. His assessment acknowledges that German armor can no longer provide adequate protection against American fighters equipped with advanced ammunition. The intelligence analysis of recovered American projectiles reveals manufacturing techniques that German metallurgists consider impossible given previous assessments of American industrial capability. The precision required for tungsten carbide core production and incendiary compound integration suggests systematic American advancement in military materials science. German test pilots conducting emergency evaluation flights against captured American ammunition confirmed that existing armor protection cannot defeat advanced projectiles at any combat range. These tests validate pilot reports while demonstrating that German armor effectiveness has been completely eliminated through American technological development. Flight training programs require immediate modification, as German instructors must teach defensive techniques that assume armor ineffectiveness rather than the aggressive tactics that armor protection had previously enabled. This tactical transformation forces fundamental changes in German fighter employment that reduce their offensive capabilities. Medical facilities treating German pilots wounded by American ammunition document injury patterns that indicate projectile fragmentation inside aircraft cockpits after armor penetration. These medical reports provide additional evidence of American ammunition effectiveness, while revealing the inadequacy of German protective systems. The psychological counseling of German pilots reveals widespread anxiety about combat survival now that armor protection cannot be relied upon for defense against American fire. Flight surgeons report increasing cases of combat fatigue related to the loss of confidence in aircraft protection systems. German aircraft manufacturers receive urgent requests for improved armor systems capable of defeating American advanced ammunition, but preliminary analysis suggests that weight requirements would make such protection impractical for fighter aircraft. The technical challenges of countering American ammunition exceed German materials science capabilities. Production planning for German fighters faces the dilemma of whether to continue installing armor that no longer provides adequate protection or to eliminate defensive weight in favor of improved performance. Either alternative represents abandonment of the protection philosophy that had characterized German fighter design. Pilot letters and diary entries document the psychological transformation from confidence in German technological superiority to recognition that American industrial capability can overcome German advantages through systematic development and mass production. These personal accounts reveal the human cost of technological obsolescence. Intelligence assessments attempt to determine the extent of American advanced ammunition deployment and production capability. German analysis suggests that American industrial capacity can produce tungsten-cored projectiles in quantities sufficient to equip all fighter aircraft, eliminating any hope that advanced ammunition represents limited special weapons. The strategic planning implications require German air commanders to reassess fighter tactics, training programs, and industrial priorities based on the assumption that American ammunition superiority will continue and expand. This strategic adjustment acknowledges fundamental changes in the technological balance of aerial warfare.
As autumn 1943 progresses, German pilots face the devastating realization that their trusted armor protection has become a liability rather than an asset, with American .50 caliber ammunition penetrating German fighter armor that had seemed impregnable just weeks before. The tungsten-cored projectiles that German intelligence never detected have eliminated German defensive advantages while creating psychological terror that extends throughout the Luftwaffe. But this technological shock represents only the beginning of American ammunition development that will revolutionize aerial warfare through industrial chemistry and precision manufacturing. How will German aviation attempt to counter American ballistic superiority? What desperate measures will German pilots employ when their aircraft become death traps rather than protective cocoons? Throughout October 1943, German aviation engineers face an unprecedented crisis as they struggle to develop armor systems capable of defeating American tungsten cord ammunition that has rendered existing fighter protection obsolete. The technical challenge involves creating defensive systems that can stop projectiles with kinetic energy exceeding anything German metallurgy had previously encountered, while maintaining the weight and size constraints necessary for fighter aircraft operation. Professor Ernst Heinkel, founder of Heinkel Aircraft Company, leads emergency research programs attempting to develop revolutionary armor materials capable of defeating American advanced ammunition. His team experiments with laminated steel plates, ceramic inserts, and exotic metal alloys that might provide protection against tungsten carbide penetrators, but preliminary testing reveals that effective protection would require armor weights exceeding 200 kilograms, impossible for fighter aircraft to carry while maintaining combat performance. The Krupp Steelworks, Germany's premier armor manufacturer, receives urgent contracts to develop improved fighter protection despite facing raw materials shortages that prevent optimal steel production. Their metallurgists experiment with heat treatment processes that might increase armor hardness beyond current levels, but discover that increased hardness creates brittle failure modes that prove even more dangerous than simple penetration when struck by high-velocity projectiles. Dr. Ferdinand Gorsch's research facility conducts classified experiments with composite armor systems that combine multiple materials in layered configurations designed to defeat tungsten projectiles through energy absorption rather than simple hardness. These experimental systems show promise in laboratory testing, but require manufacturing techniques and materials that German wartime industry cannot provide in quantities necessary for operational use. German aircraft designers face the fundamental dilemma that effective protection against American ammunition requires armor weights that eliminate the performance advantages German fighters need to remain competitive in air-to-air combat. The mathematics of armor protection versus aircraft performance create impossible choices between pilot survival and mission effectiveness that no engineering solution can resolve within existing technological constraints. The examination of American tungsten cord ammunition recovered from crashed German aircraft reveals manufacturing precision that German industrial analysis considers impossible to achieve in mass production. The consistent quality of American projectiles suggests manufacturing capabilities that exceed German precision engineering while maintaining production rates that German industry cannot match under wartime conditions. Alternative approaches to pilot protection include improved ejection seat systems and cockpit escape mechanisms that might enable pilot survival even when armor fails. These emergency systems face development challenges as German resources become increasingly constrained while American ammunition continues improving through ongoing research and development programs. Intelligence-gathering efforts attempt to identify American ammunition production facilities and development programs that might be disrupted through bombing campaigns or sabotage operations. German analysis reveals that American ammunition production is distributed across multiple facilities with redundant capability, making disruption impossible through available German strategic bombing resources. The psychological impact on German engineering personnel proves as significant as technical challenges, as professionals trained in German technological superiority must acknowledge that American industrial chemistry has achieved advances that German science cannot match. This recognition affects morale and creativity in research programs while forcing acceptance of American technical leadership in critical areas. Training programs for German pilots undergo emergency revision to emphasize survival techniques when armor protection fails,
including improved bailout procedures and emergency landing techniques. These training modifications acknowledge that technical solutions may not restore armor effectiveness, requiring pilots to adapt to permanent changes in their survival odds during combat operations. German medical facilities prepare for increasing casualties as armor failure creates wound patterns that German flight surgeons have never encountered. The medical preparation includes specialized surgical techniques for treating tungsten fragment wounds and burns from incendiary compounds that penetrate cockpit protection systems. Industrial planning requires German aircraft manufacturers to decide whether to continue installing ineffective armor or to eliminate protective weight in favor of improved aircraft performance. Either alternative represents fundamental changes to German fighter design philosophy while acknowledging the failure of previous protection concepts.
By late 1943, American ammunition manufacturers have perfected production techniques that enable mass manufacturing of tungsten-cored .50 caliber projectiles, transforming what began as specialized rounds into standard equipment for American fighter aircraft throughout Europe and the Pacific. This industrial achievement creates sustained American advantages that compound over time as German armor becomes increasingly ineffective against improving American ballistics. The Winchester Repeating Arms Company's conversion to military ammunition production demonstrates American industrial flexibility as civilian manufacturers adapt their precision capabilities to military requirements. Winchester's production lines manufacture .50 caliber armor-piercing incendiary rounds with consistency that exceeds German quality control standards, while achieving output rates that German ammunition plants cannot match, even under optimal conditions. Technical improvements to American incendiary compounds create projectiles that ignite more reliably after armor penetration, while burning at higher temperatures that cause more extensive secondary damage to aircraft systems. These chemical advances ensure that armor penetration results in aircraft destruction rather than merely pilot casualties, maximizing the tactical effectiveness of each successful hit. The integration of American ammunition development with combat feedback creates continuous improvement cycles that refine projectile performance based on operational experience. American ammunition engineers receive detailed reports from fighter pilots describing ammunition effectiveness against various German aircraft types, enabling targeted improvements that address specific tactical requirements. Quality assurance programs ensure that American ammunition maintains consistent ballistic performance despite mass production requirements that prioritize quantity over individual projectile optimization. Statistical sampling techniques identify production variations before they affect operational ammunition supplies, maintaining reliability standards that enable pilots to depend on their weapons' effectiveness. The development of specialized .50 caliber variants for different tactical applications creates ammunition types optimized for specific targets while maintaining interchangeability with standard aircraft machine gun systems. These specialized rounds include enhanced penetrators for heavily armored targets and improved incendiary loads for fuel system ignition, providing tactical flexibility that German ammunition variety cannot match. American metallurgical research produces tungsten carbide cores with improved hardness characteristics that maintain penetration capability at extended ranges where German armor might otherwise provide adequate protection. These materials improvements extend the effective engagement envelope for American fighters while reducing the range advantages that German armor had previously provided. Supply chain management ensures that American fighter squadrons throughout Europe receive adequate quantities of advanced ammunition for operational use, rather than emergency reserves only. This logistical achievement enables routine employment of tungsten-cored projectiles against all suitable targets, maximizing the tactical impact of American ballistic superiority. Industrial coordination between ammunition manufacturers and aircraft producers ensures that American fighter armament systems optimize the effectiveness of advanced projectiles through improved gun installations and ammunition feed systems.
This systematic approach maximizes ammunition performance while maintaining the reliability necessary for combat operations. The economic analysis of advanced ammunition production demonstrates that American industrial capacity can absorb the material costs of tungsten carbide cores while maintaining production rates that support expanding military requirements. This economic advantage enables sustained technological superiority that German resource limitations cannot match under wartime constraints. Research institutions throughout the United States contribute to ammunition development through academic programs that provide theoretical foundations for practical improvements. University research in ballistics, metallurgy, and chemistry supports military ammunition programs while ensuring continued American leadership in projectile technology. International cooperation with British and other Allied ammunition programs creates knowledge sharing that accelerates development while providing alternative production sources for critical materials. This collaborative approach ensures ammunition availability even if individual production facilities face disruption through enemy action. The systematic failure of German armor protection creates cascading effects that extend far beyond individual pilot casualties to fundamental changes in German fighter tactics, training programs, and strategic planning. German air operations must adapt to the reality that their fighters can no longer survive exposure to American defensive fire, forcing defensive approaches that reduce German offensive capability while failing to prevent continued losses. General Major Adolf Galland, commanding German fighter forces, issues tactical directives acknowledging that German pilots can no longer rely on armor protection during combat operations. His orders require German fighters to avoid prolonged engagements with American aircraft while emphasizing surprise attacks that minimize exposure to American defensive fire, tactical constraints that reduce German operational effectiveness while failing to address underlying technological disadvantages. Flight training programs undergo complete revision, as German instructors must teach defensive techniques that assume armor failure rather than the aggressive tactics that armor protection had previously enabled. New pilots receive training that emphasizes survival over mission accomplishment, creating psychological effects that reduce combat effectiveness even before pilots encounter American ammunition in operational conditions. German fighter production faces impossible choices between continuing ineffective armor installation or eliminating protective weight that might improve aircraft performance. Production managers discover that removing armor saves weight but creates pilot morale problems, while maintaining armor provides false confidence that proves lethal in combat against American fighters. The statistical analysis of German fighter losses reveals casualty rates that approach unsustainable levels, as American ammunition effectiveness eliminates the survival advantages that German pilots had previously enjoyed. Monthly losses exceed pilot training capacity while destroying experienced aircrew whose combat knowledge cannot be replaced through accelerated training programs. Medical facilities treating German fighter pilots document wound patterns that demonstrate the devastating effectiveness of American incendiary compounds after armor penetration. Flight surgeons report that pilots surviving tungsten fragment wounds often suffer permanent disabilities that eliminate them from combat duty, reducing the effective pilot pool beyond simple casualty statistics. Intelligence assessments conclude that American ammunition superiority will continue expanding as industrial production increases and technical improvements continue. German analysis indicates that ammunition effectiveness will improve while availability increases, creating permanent American advantages that German countermeasures cannot overcome through available resources or technology. Maintenance requirements for German fighters increase dramatically as aircraft surviving encounters with American ammunition require extensive repairs to systems damaged by incendiary effects. Ground crews report repair times that exceed aircraft replacement schedules, creating maintenance backlogs that reduce operational aircraft availability below nominal strength figures. Communication systems between German fighter units and ground controllers developed new procedures for managing engagements against American fighters equipped with armor-penetrating ammunition. These procedural changes emphasize rapid disengagement and mutual support techniques that reduce individual pilot exposure while limiting German offensive options. German pilot morale deteriorates as aircrew lose confidence in their aircraft's protective systems while facing American opponents whose ammunition can defeat any German defensive measures. Squadron commanders report increasing reluctance to engage American formations and growing requests for transfer to bomber or transport units that avoid direct fighter combat. Training accidents increase as German pilots attempt to master defensive techniques that require precision flying under stress conditions. The complexity of survival tactics against American ammunition creates training challenges that exceed available instructor capability while consuming flight time and fuel that operational requirements cannot spare. Strategic planning for German air operations must account for permanent American ammunition advantages that render previous tactical assumptions obsolete. German commanders develop alternative approaches to air warfare that emphasize avoiding American fighters rather than defeating them, acknowledging technological inferiority that cannot be overcome through tactical innovation alone.
The realization that American ammunition can penetrate German fighter armor creates profound psychological effects that extend throughout the Luftwaffe, affecting not only frontline pilots, but also ground crews, engineers, and commanders, who must confront the failure of technological systems they had considered invincible. The human dimension of technological obsolescence proves as devastating as the physical threat itself. Hauptmann Klaus Weber, now grounded due to wounds received from tungsten fragments that penetrated his cockpit armor, writes detailed reports describing the psychological transformation from confidence in German superiority to recognition of American technological dominance. His analysis emphasizes that pilot morale collapse may prove more damaging to German air operations than the physical casualties caused by improved American ammunition. Flight surgeon Dr. Heinrich Braun documents the increasing cases of combat fatigue and anxiety disorders among German pilots who have lost confidence in their aircraft's protective systems. His medical reports describe symptoms that exceed normal combat stress reactions, including panic attacks triggered by the sound of aircraft engines and nightmares involving armor penetration scenarios that prevent restful sleep. German pilot training instructors report difficulty maintaining student morale when teaching defensive techniques that acknowledge the inadequacy of German protection systems. New pilots entering operational training display hesitation and fear that reduces their learning effectiveness while creating safety hazards during formation flying and combat maneuvering exercises. Personal letters and diary entries from German pilots revealed the psychological impact of discovering that American technology has surpassed German capabilities in critical areas. These private communications describe feelings of betrayal by German propaganda claims of technological superiority, while expressing doubt about German ability to continue effective resistance against American industrial might. Squadron commanders implement counseling programs attempting to address pilot anxiety about armor effectiveness, but discover that psychological support cannot overcome rational fears based on accurate assessment of technological disadvantages. These counseling efforts often increase pilot awareness of their vulnerability rather than restoring confidence in German protective systems. The examination of destroyed German aircraft reveals that armor failure often creates secondary hazards as tungsten fragments ricochet inside cockpits, creating multiple wound sites and structural damage that compounds the effects of initial penetration. These forensic studies provide evidence that armor has become a liability rather than protection under current combat conditions. Veteran pilots request transfers to other aircraft types or non-combat assignments, as the reality of armor ineffectiveness eliminates their willingness to continue fighter operations. These transfer requests remove experienced aircrew from fighter squadrons while acknowledging that technological changes have made fighter combat unsurvivable for rational individuals. As 1944 begins, with German fighter losses reaching critical levels, Luftwaffe leadership implements increasingly desperate measures attempting to restore some degree of pilot protection against American ammunition that has rendered conventional armor obsolete. These emergency programs represent the final attempts to overcome American technological advantages through alternative approaches that acknowledge the failure of traditional armor systems. The development of standoff weapons for German fighters attempts to enable engagement of American aircraft beyond the range of defensive machine gun fire. Projects including air-to-air rockets and cannon with extended range provide theoretical alternatives to close combat, where American ammunition proves most devastating. But these weapons suffer from accuracy problems and limited availability that prevent widespread deployment. Experimental programs investigate radical approaches to pilot protection, including ejection seats that enable survival even when aircraft armor fails. These emergency escape systems face development challenges as German resources become constrained, while technical requirements exceed available materials and manufacturing capability under wartime conditions. Tactical innovations emphasize high-speed hit-and-run attacks that minimize exposure to American defensive fire, while attempting to achieve combat effectiveness through surprise rather than sustained engagement. These tactical changes require pilot training modifications and aircraft performance improvements that German industrial capacity cannot provide while maintaining existing production schedules. Specialized German units receive priority equipment and training for operations against American formations, attempting to achieve tactical success through elite pilot capabilities rather than technological advantages. These specialized squadrons suffer disproportionate casualties while failing to achieve strategic results that justify their resource requirements. Diplomatic efforts attempt to acquire advanced materials and manufacturing techniques from German allies or neutral countries that might enable improved ammunition or armor production. These diplomatic initiatives reveal that American technological advantages extend beyond individual innovations to systematic industrial capabilities that other nations cannot provide to Germany. Sabotage operations target American ammunition production facilities and research laboratories in attempts to disrupt development programs that continue improving American ballistics capabilities. These operations achieve minimal success while consuming intelligence resources that might provide more valuable information if applied to other intelligence targets. Research cooperation with Japanese allies attempts to share technological developments that might address common ammunition and armor challenges, but reveals that Japanese industry faces similar limitations while lacking materials and manufacturing capabilities necessary for advanced projectile production. The psychological preparation of German pilots includes fatalistic training that acknowledges high casualty probabilities while attempting to maintain combat effectiveness despite technological disadvantages. This training approach creates morale problems while failing to address underlying survival issues that rational pilots cannot ignore during combat operations.
The systematic defeat of German fighter armor by American .50 caliber ammunition represents one of the most significant technological transformations in military aviation history, establishing principles of defensive systems design, ammunition development, and industrial warfare that continue influencing military technology development into the modern era. The lessons learned from this technological revolution shaped post-war military research priorities and international competition in advanced material science. American ammunition development philosophy established through the Tungsten carbide program emphasizes systematic improvement of existing weapons through advanced materials rather than revolutionary new weapon systems. This approach influences modern military technology development that achieves decisive advantages through incremental improvements to proven systems rather than completely new weapon concepts that require extensive development time.
The industrial lessons of American ammunition production demonstrate the strategic importance of material science and precision manufacturing capability in achieving military advantages that cannot be countered through tactical innovation alone. Modern military planning continues emphasizing industrial capacity and technical education as foundations for sustained competitive advantage in advanced technology development. German armor failure analysis provides case studies for modern defensive systems design that must account for continuing offensive improvements rather than static threat assessments. Contemporary armor development incorporates lessons learned from German experiences with technological surprise, ensuring that defensive systems maintain effectiveness against evolving threats through systematic upgrade capability. Research institution integration with military development programs, exemplified by American academic contributions to ammunition development, establishes models for modern military-industrial academic cooperation that accelerates innovation while ensuring practical application of theoretical advances. This collaborative approach continues characterizing advanced technology development that requires interdisciplinary expertise. The economic analysis of advanced materials production provides frameworks for modern military procurement that must balance performance advantages against resource costs while maintaining sustainable production capability. These economic considerations influence contemporary defense planning that must optimize capability development within budget constraints and industrial limitations. Strategic implications of materials science superiority demonstrate how advantages in fundamental technologies can provide decisive military benefits across multiple warfare domains. Modern military strategy continues recognizing materials research and advanced manufacturing as critical elements of national security that require sustained investment and protection from foreign competition. The documentation of German technological surprise provides historical examples for modern intelligence assessment that must identify emerging technologies before they achieve operational deployment. Intelligence communities continue studying the German armor failure as a case study in technological surprise that provides lessons for contemporary threat assessment methodologies. Educational programs studying advanced ammunition development provide technical foundations for modern ordnance engineering that must address increasingly sophisticated defensive systems. Engineering schools continue teaching ballistics principles and material science applications using historical examples that demonstrate the practical importance of theoretical knowledge in military applications. The systematic penetration of German fighter armor by American .50 caliber tungsten cord ammunition marks the end of an era when defensive protection could provide reliable pilot survival against improved offensive systems. This technological transformation demonstrates how industrial capability combined with systematic research can overcome established defensive advantages through sustained development programs that achieve decisive tactical advantages. The personal stories of German pilots who experienced armor failure provide human perspectives on technological change that renders professional expertise and equipment obsolete within remarkably short periods. These individual experiences demonstrate how technological innovation can transform warfare faster than military organizations can adapt their tactics, training, and psychological preparation for changed combat conditions. The industrial achievement represented by American mass production of advanced ammunition establishes precedents for military-industrial mobilization that continue influencing modern defense planning and resource allocation. The demonstration that sustained research and development can overcome seemingly permanent technological advantages provides strategic lessons that remain relevant for contemporary military competition. The technical innovations developed during American ammunition programs establish ballistics and materials science applications that continue influencing modern ordnance development. Contemporary ammunition designers continue studying tungsten carbide projectiles and incendiary compounds as foundations for advanced projectile development that addresses modern defensive systems. The strategic consequences of American ammunition superiority demonstrate how advantages in fundamental technologies can influence broader military operations through cumulative effects that extend beyond immediate tactical applications. The elimination of German pilot protection
enabled subsequent air operations that would have been impossible under conditions of effective German armor protection. The international implications of American technological leadership, established through ammunition development, influence post-war military relationships and technology transfer arrangements. The demonstration of American materials science and industrial capability creates strategic advantages that continue affecting international relations and alliance structures decades after the immediate military applications end.